Dear friends, welcome. Today in this lecture we are going to start the study of vector calculus, and in this we shall study the first chapter of differential operators. In this chapter we shall study the scalar point functions, vector point functions, their limits and their directional derivatives along coordinate axis and along any line. Then we are going to study the differential operators, del operator, then gradient of a scalar point function, divergence of and curl of vector point function and their properties. So first we shall see what is the scalar point function and vector point function. If R is a region, any region of space that can be denoted by R, and if P is a point in this region, then if there is a scalar quantity which is associated with this point P and that we can denote by phi P, then this phi of P is called a scalar point function at point P. So for example, if you consider this region, and if P is a point in the region, and if you associate a scalar quantity as temperature, then that phi of P will represent temperature at point P. So if there is another point Q, then phi of Q will be temperature at point Q. Temperature is a scalar quantity and therefore that function will be scalar point function. Similarly, if you consider density, then that will also be a scalar quantity, and that if it represents phi represents density, then it will be a scalar point function, and so on. So similar to this, we can consider another function that which is a vector. We know scalar, the difference between scalar and vector. Scalar has only magnitude, while vector has magnitude and as well as direction, and therefore we denote, we associate a vector quantity and we denote it by f bar, or some in books it is denoted by bold letter, capital bold letter f. So f bar of P will represent a vector point function at P. And for example, vector point function may be velocity at time t, or acceleration or force, etc. These are vector quantities, and these will be scalar quantities, which are temperature, mass, density, etc. If these are associated with the point, then if the quantity is scalar, the function will be called scalar point function. Why it is called point function? Because it is defined at a point, particular point P, a value at that point, and therefore it is a scalar point function, or similarly a vector point function if the quantity is vector quantity. And further we may have limit of scalar point function and vector point function. Suppose, so we will see the meaning of this limit of scalar point function of phi of P. And suppose this phi of P quantity, we say phi of P approaches a quantity L if phi P tends to L. If, see, for the difference, if given epsilon greater than 0, or we may, if given epsilon greater than 0, there exists delta greater than 0, such that the absolute difference between these two quantities phi P and L is less than epsilon whenever the distance between P and A, phi P tends to L as, or if as P tends to A is to be considered whenever the distance between P and A is less than delta. So this is the usual definition of a function. When we say function tends to L as x tends to A, if given epsilon greater than 0, epsilon and delta are Greek letters denoting small quantities, positive. Epsilon greater than 0 means positive quantity. There exists another positive quantity or corresponding to this epsilon, delta greater than 0. Whenever the difference or absolute difference of this phi p and L is less than epsilon, the distance between P and A is less than delta, or that can be considered as if you have A as a center, a sphere having radius delta, then P lies within this sphere is the meaning of this. Whenever P is close to A, phi p will be close to L. That is the meaning of limit, as in usual function f of x. So, this is the limit of scalar point function phi of p. Similarly, limit of vector point, and we write this as limit p tends to A of phi of p is equal to L. So, this absolute difference of this is less than epsilon whenever absolute difference of this is less than delta. And similarly, we can say limit p tends to A of vector point function f bar of p is equal to L if the absolute difference of phi p f bar p and L is less than epsilon whenever the distance between p, I have denoted the distance between p and A by rho, which is a metric, is less than delta. Or that can also be considered if it is a line, then that will be mod of p minus A. Absolute difference of p and A is less than delta is the meaning, but it is not a line, may be a region in space, and therefore we measure the distance by rho is less than delta, and that is the notation for limit. Limit of phi p is L as p tends to A, p approaches towards A. So, this we denote for scalar point function and this we denote for vector point function. So, only the difference in notation is scalar we are denoting by this Greek letter phi of p, and for vector we are using f bar. Bar denotes vector quantity. So, and this is a necessarily will be a vector. F bar p will tend to L bar as then this difference, absolute difference of these two is less than epsilon whenever the difference between p and A is less than delta. So, this is the meaning of limit. Now, we shall see the derivative of scalar point function, but this derivative will be taken along a particular direction, and therefore, the derivative is known as directional derivative. Derivative of a scalar point function. Function phi. Let phi p be a scalar point function at point p. We consider a semi-line AP. Semi-line AP, semi-line means line in one direction. Suppose this is A point and this is P point, then the line will be from A to B, or a ray from A to P. And see if then the limit, then the limit as limit P approaches A, phi of P minus phi of A divided by AP, if it exists. Is called the derivative or the directional derivative. directional derivative of phi see this is the directional derivative of phi at A along the line or along the semi line AP. Now you see this is similar to usual derivative. So what is the definition of if f is a function of x, then how we define f dash of x? We have mean definition for f dash of x, limit x tends to c f of x minus f of c divided by x minus c. So this is the definition for derivative f dash of x, or if we can consider is this x minus c as h, then that will be limit h tends to 0 f of x plus h minus f of x divided by h. That is the definition of derivative, or it is similar to this one. And as the same we have defined limit p tends to a, instead of x and c, here the points are a and p. So this point tends to a, the distance between a and p is small. Then the values of function at p minus function at a, that is f of p minus phi of p minus phi of a divided by the distance ap. So this is the directional derivative that of a scalar point function along the direction a to p. The direction is also important here. Now similarly, what will be the directional derivative of scalar point function, a vector point function phi, vector point function f? Similarly, the directional derivative of vector point function of a vector point function, which we denote by f bar at point a along the semi line AP is limit p tends to a, only phi is to be replaced by f bar. Here it is phi, scalar point function, and here now it is vector point function. That will be f bar of p minus f bar of a, or at a, divided by ap. So see, here we have used phi notation for scalar, here we have used f bar notation for a vector quantity. So this is the definition for directional derivative of a scalar point function and directional derivative of a vector point function. Now we shall consider directional derivative of a scalar point function along coordinate axis. So this is along the coordinate axis. And for that purpose, we first consider the directional derivative along positive coordinate axis we shall consider, and for that purpose we shall draw this figure. Suppose these are the axes. This is x axis, this is y axis, and this is z axis. And we want to consider the directional derivative along x direction, positive x axis means this direction, and therefore we take a line AP along which is parallel to x axis. But before that we will denote these scalar point functions and vector point functions at a particular point. That means if you consider the point P as say xyz, coordinates of P as xyz, then phi P will be equal to phi of xyz. Or if A is the point as xyz, then phi of A is equal to phi of xyz. or different points may be considered x1, y1, z1, etc. So thus these will be scalar point function at coordinate x, y, z, and the point A has coordinates x, y, z, then it will be phi of x, y, z. If the point P has coordinate x1, y1, z1, then it will be phi of P is equal to phi of x1, y1, z1. So this is the values of the scalar point function. Similarly, the vector point function at a particular point having coordinates x, y, z. Now here also let A be the point. Let A, the coordinates of A be x, y, z, and now let AP be parallel to the positive x axis or to the x axis, parallel to the x axis, and in the direction A to P. Let P be a point on this line. So what will be the coordinates of P? See, only x coordinate will change, y and z coordinate will remain the same because the line is parallel to x axis. And let P be having coordinates x plus delta x, y and z. So these will be the coordinates of A and P. Means A having coordinate x, y, z, P will have coordinate x plus delta x, y and z. Y and z coordinate will remain the same because the line is parallel to x axis. Only x coordinate changes. Now thus the derivative, now we want to consider the derivative of scalar point function phi. So then the derivative, then the directional derivative. Derivative of scalar point function phi, or simply we say scalar function phi at A point, that is x, y, z, is, earlier definition we shall use, is limit P tends to A of phi of P minus phi of A divided by PA or AP. So this is the by definition it is, but this is equal to limit. Now you see, as P tends to A, P approaches to A, means distance AP becomes smaller and smaller, and in that case the coordinates approach this x plus delta x will approach to x, means delta x will become closer to 0 or delta x approaches 0. So therefore P tends to A means delta x tends to 0. And what is phi of P? Phi of P will be phi of, what are the coordinates of P? These are x plus delta x, y, z, minus phi of A. The coordinates of A are x, y, z, divided by AP. Now what is the AP distance? See, this is delta x, because the coordinates of A are x, y, z, and P are x plus delta x, comma y, comma z, and therefore AP is delta x. That means this distance is delta x, and P tends to A means delta x tends to 0, and divided by delta x. AP is delta x. So what this represents? See, this is a function of 3 variable, and only there is change in x variable, and y and z are constants. So therefore this is the derivative which is with respect to x, keeping y and z constant, means it is a partial derivative of phi with respect to x. So this is equal to, partial derivative notation we have used this, dou phi by dou x. So thus the directional derivative of phi along positive direction of x axis, the directional derivative of phi at A x y z along positive direction of x axis, along positive x axis, positive direction of x-axis. This is limit p tends to a. We have considered the positive direction along x-axis, or direction which is parallel to x-axis means along the same direction of positive x-axis, and therefore it is limit p tends to a phi p minus phi a divided by ap, and which we have expressed as dou phi by dou x. Thus directional derivative of scalar point function phi along positive direction of x-axis is partial derivative with respect to x. Similarly, we can get the result as the directional derivative of phi along positive y-axis will be dou phi by dou y, and directional derivative of phi along positive direction of z-axis will be dou phi by dou z. So that we shall write. So similarly, the directional derivative of phi along y and z axis, positive y and z axis. I will continue here only. Similarly, the directional derivatives of a scalar point function phi along the positive directions of y and z axis are dou phi by dou y, because we have obtained the result for the positive direction of x axis. Function is phi and we get dou phi by dou y. Here what will happen if you consider positive direction of y axis, y will change, x and y coordinate will change and x and z coordinate will remain the same, and therefore there will be increment in y, x z remains the same, divided by the increment. If you consider delta y, then that will be dou phi by dou y, and along z axis, positive z axis, it will be dou phi by dou z respectively. So this we shall remember. Similarly, the directional derivative of vector point function along positive coordinate axis x, y, z will be, or we can write similarly the directional derivatives of a vector point function f bar at this point x, y, z along the positive directions, because here the direction is important. If you consider negative direction of coordinate axis, then the derivative will be negative. So along the positive direction of x, y, z axis are dou f bar by dou x, dou f bar by dou y, and dou f bar by dou z respectively. Only we have to change phi by f bar. Exactly same result we shall obtain. So these are the directional derivative of scalar point function and vector point function along the coordinate axis. Now in our next lecture we shall obtain the directional derivatives of the scalar point function and vector point function along any line. So here we have obtained along the coordinate axis, and if the we have to consider instead of positive direction, if you consider negative directions, then these derivative will be negative. So because the direction is reversed. So remaining part we will continue in our next lecture. Thank you.